Okay, so so I was asking for Matthew. Do you have a microphone? Okay, Jacob. All right. So 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 both Patrick and Jake would just stand by. So I'm gonna do the scenario that I had there called slow start. So I'm gonna plot here a piecewise linear function, and for simplicity, so here I go with the first. So I'm gonna say 0.1. I'm gonna use this slope, and just for simplicity of plotting this, I'm gonna assume that the intercept is 0. Okay, so we'll do something with a non-zero intercept for the last case that we work on today. But so here, I'm gonna say this is gonna go from 1 to maybe, I don't know, 14. Okay, so let's see what that is looking like. So, okay, so maybe this is too long. So maybe 1 through 7. And now I'm gonna go with the other branch here. I'm gonna say that this would be 1.1x, and this will go between 7 and maybe 14. Okay, so let's see what that is looking like. Okay, so that looks like that. And then the last branch, y equals 0.05. This is completely me choosing the values of every linear function here. So, but it's for illustration purposes. So this would be for x bigger than 14. So I can say just x bigger than 14. Well, maybe we can have it x between 14 and, I don't know, 30. Okay, so let's see what that looks like. Yeah, so this is giving us this. After you type the equations, you can click this and that goes to the side. And so here we have a picture. It's not exactly the same shape that I had there in the slide where I was writing, but it's very similar. So the main thing to note is that the slope, you can see the slope here, it takes a value of 0.1. The second value is a lot larger than the very first value of slope, and the third value is the smallest of the three values of slope. Okay, so and that what I'm trying to illustrate here is the shape. If I were going to complete each of those lines with an intercept, then it's just simpler right now to picture it. It's the main message is what the shape of the line looks in relation to the slope, and for you to start differentiating what does it mean to have a really small value of slope. So if we make that even smaller, like 0.01 or 0.01, so you can see that under some resolution, that graph there that appears in green there, it looks very flat, almost as if it were a zero slope. It's not zero, right? So we were using the value of 0.05, and so you can see some incline. So all three values of slope are positive, and yeah, so this is where, Patrick, are you ready to share your screen? You're going to do
Yep.
a representation of the fast start. Um, okay, so oh, you already did it. Okay, I was gonna tell you what values to use, and you okay. So I'm gonna ask you. Here are a few things that we can draw out of here. First is that the branch, a very important part of the branches is the time subdomains. So the subintervals in the horizontal axis, which is precisely what you're writing in between braces, right? In Desmos. So a thing that I don't know if that's how you did it, but you need to know the slope, but then you start playing with the intercept to make them match. So what you have on the screen right now, Patrick, is a okay. You just made a change there just by moving that last green linear function. You there is a jump. Okay, so at first it was a continuation, so it continues from red to blue, and it was a continuation from blue to green, and now there is a jump from blue to green. That jump is called jump discontinuity. Okay, I think last week there were, or 2 weeks ago, there was something called removable discontinuities. Well, this is another type of the discontinuity means that in the graph, the function is going to have some piece of the graph that supposed to be there, but something strange happens at that location. And here, what happens is there is a jump. Okay, so whether that was the green, so that's 7.65. So hold on, Patrick. So you have um, so what happens in the blue, what happens with the green if you just remove 765? We're gonna mess this up and your graph looks really beautiful. Okay, so maybe it's not bad. And so what happens with the blue if you remove 6.3? Okay, so there you have 3 segments, each of them with a different slope. They have these substantial jump discontinuities. If these were measurements of cases, the story here would not be that bad, because you would be, I don't know, on day 7 after the first week, going from first to second week, you do see a decline, um, but more importantly, you're going to see a slower pace in the second week than on the first week, right? So here, the fact that the very first line has a slope with the largest value, that's why that is very, very inclined at the beginning, right? And then going into the third week, so it goes from fast to slower to slowest. The third week, the pace, the rate of change would be the smallest of the 3 values, and it would it would still increase, but not exactly at the very fast pace of the very first seven days here, assuming that the x values is measurements of one day, right? And then Patrick, you can put back the blue line had a 6.3. That was the intercept. You can put that back, and the green was 765, but I don't know what was the original value there. 769.
That's yeah. That's how I was figuring it out.
Okay, so let me I'm gonna ask you to do that again. So for both the blue and the red, so you first decide on the values of the slope, and then you have to decide what intercept do I use so that this matches. And what you are saying with your intuition was put the cursor in Desmos. You can put the cursor in a specific point in the graph, and it tells you the ordinate pair, right?
Mhm.
And so from that ordinate pair, you see that the y coordinate is 7.697, and that's how you decided for the blue line to be the intercept. No, that was the intercept of the next line, right? Seven.
Yep. It would be this was 6.98, so I figured it was 7, but for some reason 6.3 lines up. I didn't do the
Yeah,
actual math.
yeah. If you do the actual math, you'll be exact. But
Yeah.
this is something about trial and error. It doesn't have to be like a perfect continuation, but it can get close enough. And then yeah, so there. But that was really good. Okay, thank you.